Welcome back. This is video lecture 30.1, part 2. And we're going to now talk about an idea associated with electromagnetic induction. And let me try to motivate for you why this is an important idea. When we had a regular electric circuit with a traditional source of EMF, like a battery, and conducting wires and a resistor, something very basic, like, I'll draw a circuit diagram over here. As we know, that symbol represents the source of EMF, conducting wires, and the resistor R. And we use the symbol curly E, and we needed to keep track of the polarity, it's called, of the EMF, because that's going to tell us which way the conventional current flows around the loop, clockwise in that case. But of course, if I reverse the polarity of the EMF source, which you can do, like that, that's a reversed polarity. That's the high potential side, that's the low potential side. The arrow points that way. Then the conventional current that we're talking about goes the other way. Right? What's called the polarity of the EMF determines the direction the current goes around the loop. Well, we are going to have that issue now, except we're now talking about a loop where there's no traditional source of EMF, but there's a changing magnetic flux through the area, the surface inside the loop, and that will give us an induced EMF. And we need to know the polarity of that induced EMF. Is it such as to drive conventional current that way or that way? That's what we're talking about when we're talking about determining the polarity of the induced EMF and the induced current. Which way, in a simple closed loop like this, with changing magnetic flux through it, which way will the induced EMF polarity be? Which way will the induced current flow? We have to be able to figure that out. It turns out that's important. The problem is determining that polarity of the induced EMF and current is a little bit subtle and takes quite a bit of practice. But it basically boils down to this induction effect opposes any changes. Now that's a very broad way to say it, but it might be helpful to remember. This induction effect opposes any changes. Let me talk you through how that works in a very specific scenario, using pictures from Wiley+. All right, what we have here in the drawing on the left is an actual physical conducting loop. Somebody has made a circular wire loop, but it has no traditional source of EMF in it, in the loop. There's no battery in there. There's no power supply hooked up in that circle. So under normal circumstances, you would expect there to be no current flowing around that loop. Okay? And that loop is just held there in place. Okay? All right. Then you come along and you have picked up a bar magnet, a magnetic dipole. And every bar magnet has a north pole and a south pole. And you have oriented the poles like that, on purpose, let's say, with the north pole down and the south pole up. And then you are going to physically move the bar magnet towards the conducting loop. Much like the person in the video, in the previous video lecture, moved the bar magnet towards the big loop that was being held. All right. Now, they don't show it, but we know that bar magnet produces magnetic field, and the magnetic field lines of a bar magnet look something like this. Coming outward this way, and then upward this way, and inward to the south pole. They don't draw them, so I did. That's just some of the magnetic field lines that bar magnet, that magnetic dipole, produce. So, look what's happening then. As we bring the bar magnet closer to the conducting loop, the bar magnet's magnetic field, some of it, is piercing this surface right here inside the loop. And so I have a magnetic flux, phi sub b, through that conducting loop's surface. But because I'm moving the magnet closer, isn't the magnet's magnetic field getting stronger at the location of the loop? And therefore, don't I have a changing magnetic flux through the loop? All right, that's the first step in this kind of flowchart sequence of events. It's here at the top. I have a changing magnetic flux through a loop. In fact, I want to be a little more specific about what we have at this step. I have a magnetic flux, phi sub b, that is increasing in that conducting loop due to the fact that I'm moving the magnet closer. I describe this scenario as the flux trend through the loop. Tells me what's happening through the loop. That I've got magnetic flux through the loop, and it's increasing. And I want to add something. It's increasing flux due to a magnetic field B that is directed downward. Does that make sense? Let me erase this. That's the first step in this flowchart. And I'm talking about that conducting loop, and I'm bringing that magnet closer with the North Pole facing down, therefore the magnetic field's pointing downward from the bar magnet. And so I have a increasing magnetic flux, which is due to a magnetic field directed downward. That's my flux trend. Okay, the minute I have a changing magnetic flux, guess who stands up and says, aha? Faraday does. Oh, you said you have a changing flux? Then guess what? You'll have an induced EMF in your loop. Notice the notation, curly E sub IND. It's not a traditional source of EMF like from a battery or a power supply. It's a completely new way to make an EMF. And so we call it an induced EMF. So Faraday tells us that. All right, but now what they're telling me is that this loop, I'll draw it over here, is acting like there's a battery in it. It's acting like it, maybe like that, for example. Okay? It turns out it is like that. And it's a conducting loop made out of steel, maybe. Okay? And if I have any kind of EMF in a conducting loop, traditional or induced, I'll have current flowing. Okay? So that's just from the fact that I have a conducting loop with an EMF in it. So there'll be a current going around. Now we're going to call it induced current. Okay? Because it comes from this special kind of EMF called an induced EMF. We'll label it I sub IND. Okay? All right, now this next step is what is historically called Lenz's law. And it's the opposing part I was talking about. That induced current will create its own magnetic field. Yes? Current creates magnetic field. I've got an induced current in this loop, so I have a magnetic field. Guess what? We're going to call it an induced magnetic field. Right? There'll be an induced magnetic field due to the induced current. We'll label it B induced. And the direction of that B induced, here's the kicker. Get rid of that word there. Opposes the original flux trend that started this whole process. See how the flow chart connects back up to the top? That induced magnetic field, B induced, will be directed so as to oppose the original changing magnetic flux that started the whole thing. It's called biting the hand that feeds you, in a very loose way. So now let's look back at the picture on the left. I need to have a B induced, and that's what these magnetic field lines that are drawn represent, that is basically upward. Because I had a downward B from the magnet that produced an increasing magnetic flux. So to try to cancel out that increase in the flux, I need the B induced to be opposite to the original B, which is up. But to get a B induced up, just from the special right-hand rule, I need an I induced in the conducting loop going around counterclockwise when viewed from above, like that. And then that will give me a B induced up. Okay, there's a lot going on there. But the B induced must be upward. In this case, when my flux trend was an increasing flux due to a B downward. That's what started all this. I had an increasing magnetic flux through the loop associated with a magnetic field directed down. I end up with an induced magnetic field up. To make a contribution to the flux opposite in sign to try to cancel out that changing flux. Okay? That's going to be the sequence of steps we're going to use to figure out the direction. Right? So now I have the polarity of the induced EMF and the induced current in this scenario. Counterclockwise, you could say, when viewed from above. Okay? But we're always going to do this series of steps. I'm going to find the flux trend, and then I'm going to figure out which way the B induced has to be to oppose that trend. It's all about opposing the original change in flux that was happening. Nature apparently doesn't want the flux through the loop to change, and it's trying to prevent it. It's not successful, but it's trying. And really the only way to make any progress applying this flow chart to help us understand Lenz's law is to practice. So we're going to practice here together, and then you're going to have a class engagement. So here's a different scenario, right? We've got to give you a whole bunch of different physical situations and have you think about them. So although we call this Lenz's law, it's all about determining the polarity of the induced EMF and the induced current in a loop. So here's the scenario. In this case, we have a long straight wire that lies on a table and carries a current I. See it there? It's lying on a tabletop, carrying a current to our right, I. All right, there is also a small circular loop of wire that is being pushed across the top of the table, starting at position 1 and heading across to position 2. So you see in position 1, the loop is, if you like, above the wire in our top-down view, moving towards the wire. In position 2, that loop is below the wire, moving away from the wire. Question 1. Determine the direction of the induced current in the loop as the loop moves past position 1. Okay? All right. Remember the flow chart. We're going to go through the steps together. First, figure out what we call the flux trend. How is the flux changing? Now I'm talking about position 1, remember? All right. Well, you see the current I in the long straight wire? Isn't that producing magnetic field everywhere? Just plain old magnetic field from plain old current. All right. And do I not have magnetic field piercing the surface that is inside the loop? I think I do. Which way is the magnetic field from the wire pointing in that interior region of the loop in picture 1? Did you say coming out towards us? I'll draw it like that. An encircled dot. That represents B wire. It's coming out of the screen towards us, and it's definitely piercing that inside surface, and so I have a magnetic flux through it. Do you see why the magnetic flux is changing? It's all because I'm moving the loop closer to the wire. So isn't the B wire getting stronger? Remember the formula for the magnetic field, B of the current in a long straight wire? The closer you get to the wire, the stronger the field is. So in position 1, I'm moving that loop closer to the wire. The B wire is getting bigger. Therefore, what's happening to the magnetic flux? It's increasing, right? So here's the flux trend. I have a phi sub B that is increasing, just fit that, increasing due to a B wire that is directed out of the page. And I'm underlying the key words. Increasing flux due to a B wire out of the page. That's the flux trend. All right, I'll put bullets here. That's the first bullet. Now that I know the flux trend, Lenz's law says that I can think of a B-induced, an induced magnetic field that wants to cancel that trend. And if I've got an increasing flux due to a B in a certain direction out of the page, then to try to cancel out that increase, I'll need a B induced opposite to the original B, so into the page, or I guess maybe I should say screen. Does that make sense? All because the flux is increasing. So I have a B induced that's into the screen. And then third step is to just use a right-hand rule argument. Okay? If I have a B induced out of the page, hold your thumb out towards you like it's coming out of the page or screen, and look which way your fingers circulate. My fingers, when I hold my thumb towards me, circulate counterclockwise. No, I'm sorry, into the screen. I did it backwards. See, boy, well, you have to be concentrating. I need the B induced to be into the screen, so I need my thumb to be going away from me. And then my fingers circulate clockwise. So by the right-hand rule, I induced is clockwise around the loop. You see that? Boy, you've got to be really concentrating all the time. I induced clockwise. So it's basically a three-step process, as I suggested. Find the flux trend. Use Lenz's law to figure out the direction of the induced magnetic field you would need to try to cancel out that trend. And then just use a right-hand rule to figure out what the direction of the induced current has to be to give you the direction of the induced magnetic field you need. Got to just practice, okay? Practice, practice, practice. Let's do part 2. Okay? Determine the direction of the induced current in the loop as the loop moves past position 2. So now the loop is below the wire as we view it from above and moving away. Please note it's moving away. Of course, there's its interior surface for the loop. So we need to first find the flux trend. I'd like you to try that first for yourself. Pause the video, and then come back when you have the flux trend, and we'll talk about it. All right, let's talk our way through the flux trend, and we really can't skip any steps. So now the loop is below the wire, and the current in the wire is going to the right. So that means I know that the magnetic field created by the wire at the location of the loop in part 2 is into the screen. So now I have a B wire through the loop into the screen. Now that B is coming from the current of that long straight wire. So I definitely have a magnetic flux through the loop in position 2 with a magnetic field B wire into the screen. But I need the flux to be changing. You see why the flux is changing? Because again, the loop is being pushed in the direction of the black arrow. So now what's happening to that magnetic flux? Is it increasing or decreasing? It's decreasing, right? Phi sub B is decreasing due to B wire that is into the screen. Let's get that flux trend written down very carefully. I have a magnetic flux that is decreasing due to a B wire into the screen or page. Do you see why it's decreasing flux? Because at position 2, the loop is being moved away from the wire, and as you get farther from a wire, its B field gets weaker, smaller. And that's why the magnetic flux is decreasing, but it's all because that loop is being moved. All right, so that's the first step, that's the first bullet. The next bullet is to figure out the direction of the induced magnetic field you need. So I'd like you to practice that, please. Pause the video, think about it, opposing the change, and then when you have an answer, come back. Okay, let's talk about it. It's very important to write down the flux trend very clearly. I have a decreasing flux due to a B wire into the screen. But Lenz's law says the induction process doesn't want any change in flux. It tries to cancel the change in flux. But now my flux is decreasing. So I have to have more flux to try to make up for that. And if the B that we're talking about is into the screen, but I need more flux, then I need the B induced to be also into the screen. All right, that's a very important point. B induced then is also into the screen. Did you say out of the screen? Almost everybody does the first time. But it isn't true. You have to keep track of two things in the flux trend. Is the flux we're talking about that's changing, is it an increasing magnitude or a decreasing magnitude? And what's the direction of the B that's causing that? And if it's a decreasing flux trend, you'll need a B induced in the same direction as the original B, because you're trying not to have a decrease. And then the third step is to use the right-hand rule to get the direction of the induced current. So try that, please. Pause the video, come back when you have an answer. Okay, so this third step is just a right-hand rule, which maybe we're getting comfortable with. If I need a B induced into the screen, then I point my thumb away from me into the screen and see which way my fingers circulate, and they circulate clockwise. So I induced is clockwise around the loop. So the I induced up here is clockwise again. Okay? I really recommend you go through this three-step process. Find the flux trend in terms of how it's changing. Use that to figure out which way your B induced is, and then just use the right-hand rule to see which way the I induced has to be, because it has to go with the B induced. All right, here's some practice for class engagement. Don't rush these practice, okay? Class engagement on Blackboard. Goes like this. This figure shows three situations in which we have identical circular conducting loops. You can see them. And they're in uniform magnetic fields. And those magnetic fields are either increasing, labeled I and C, or decreasing, DEC, in magnitude at identical rates. So they're growing or decreasing at the same rate. In each situation, the dashed line coincides with the diameter. See the dashed line going right down through the middle? And the dot array indicates a magnetic field directly out of the figure, and the X array indicates a magnetic field directly into the figure. So in A, in both the upper half and the lower half, I have a magnetic field out of the screen, increasing. In B, in the upper half, I have a magnetic field into the screen and increasing. And in the lower half, I have a magnetic field out of the screen and decreasing. And in case C, in the upper half, I have a magnetic field out of the screen and decreasing. And in the lower half, I have a magnetic field out of the screen and increasing. My task is to rank the situations according to the magnitude of the current induced in the loops, biggest to smallest. So take it a step at a time. Going to look at each half and what's happening in each half, and then figure out what's happening in the whole, and do that for all three, and then rank the biggest induced current to the smallest. We'll be practicing with this in class on Friday. That's all for this video.